This is the 22-2 video lesson, and our first question is, what is resistance in an electric circuit? And resistance is very similar to friction. And so these charges are moving along, and they encounter other charges, or they encounter deformities in these wires, and so so there's friction there, and so resistance controls the flow of electric charge. And so that's what we have here, is our resistance is similar to friction. And the second question here is, how do you calculate the resistance of a wire? Well, the equation for that is R resistance equals rho times L over A. And what each variable means is this. If you have a wire, looks something like this, that wire has a certain cross-sectional area, has a certain length, has a certain resistivity is what it's called. And that resistivity is measured in ohm meters, and each material has its own resistivity. And so you'll see on your paper there that there's a list of different resistivities for different materials, and it just basically says how easy is it for electricity to pass through this particular wire. And all this will end up equaling resistance. Now, resistance is measured in ohms, and that is, again, the friction that it encounters. So if you look at this, the longer the length, the more resistance there is. The larger the cross-sectional area, the more resistance there is. So what we have here is the equation R equals rho times L over A. And so if I increase the resistivity, it makes it harder for electrons to flow through this wire, the resistance goes up. If I increase the length of this wire, there's more of this wire to pass through, and so the resistance goes up. And if I increase the cross-sectional area, though, the resistance goes down. What you've done is you've made a wider area for those charges to be able to flow through. It's easier now for those charges to flow through. So if I wanted to increase that resistance, what I would have done is made that cross-sectional area really small, and so it's a tighter space for those electrons to flow through. Now, the only type of problem that we will use this equation is if they specifically ask us for the resistance of a wire. Otherwise, any wire, we say, and this is question number 3, we always say the resistance of a wire equals 0 ohms. Now that is true, and that's because the resistance of a wire really is small compared to resistors. Resistance of a wire might be like half an ohm or 1 ohm, or maybe as large as 5 ohms if it's a really long wire, but it's not very large compared to most resistors. So we typically say that the resistance is 0. If you go over to number 4, what are some examples of other resistors? You'll see that the picture on the left is a heater, and so you can use resistors to heat things up. The picture in the middle are resistors that control the flow of current to make sure that your iPod gets the correct amount of current flowing through it. And the last one is a light-sensitive resistor, where when the lights turn on, the photons hitting that resistor actually cause the resistance of that to increase, and so the circuit doesn't flow, and so the light doesn't go on. As soon as you turn the lights off, the resistor becomes smaller, and the light will flow. Number 5 says, what is Ohm's law? Ohm's law is the equation R equals V over I. R is the resistance, V is the potential difference or voltage, and I is the current. So we have here the R, the resistance measured in ohms, V is the potential difference measured in volts, and I is the current measured in amps. And there's this relationship in a circuit that follows Ohm's law. And if we look at a circuit, here's a diagram. We have this symbol here is the battery, and this symbol here is the resistor. And if we find out what the resistor value is and the voltage drop across that resistor and what the current in that circuit is, we can use Ohm's law to help us solve problems. So here's our circuit, and this battery has a certain voltage. And if we were to take a voltmeter and measure across that battery, because voltmeters are always put in what's called parallel. They're always going across the device. This voltage might be a voltage gain of, let's say, 6 volts. This power supply puts 6 volts into the circuit. Well, we only have one resistor here, and this resistor takes energy out of the circuit, and so if we put a voltmeter here again, parallel to the resistor on either side. That's going to read 6 volts, and it's going to take energy out of the circuit. Okay, so the potential difference is 6 volts. So our V here across this resistor, the V across that resistor is 6 volts. Well, the resistance, let's say they tell us the resistance is 12 ohms. Let's go ahead and put in 12 ohms. And now we want to solve for the current. Now, the large side of the battery is positive, the small side is negative. And so we have this current flowing, going through the resistor, back to the battery. And if we go ahead, we have to put an ammeter in here to measure that current. We put that ammeter in series. We have to put that inside the circuit. The current has to flow through that ammeter. And I want to calculate what that ammeter is going to say. So I can use the R equals V over I. Plug in my values. I have 12 ohms equals 6 volts over I. And if we calculate I ends up equaling 0.5 amps. So if I put that ammeter here, it should read a value of 0.5 amps. Now I want to look at question 6. What are the graphs for Ohm's law? Well, your typical graph is this one. V is on the y-axis. I is on the x-axis. And your graph is going to be linear. It's going to be a straight line. And the slope of that graph is your resistance. And you can see that because if you look at R equals V over I, what you have here, the V is on the y-axis, the I is on the x-axis, and that's equal to the slope. So the slope is equal to resistance. You can also look at this as y equals mx plus b. And if you write out y equals mx plus b, and you plug in your values on the y-axis, we have V. The slope is R. On the x-axis, we have the current I. We're going to assume the B value is 0. And so this that equation right there is exactly the same as R equals V over I, just the variables rearranged. The other graph that you might encounter is this one here. They might go ahead and do, I've seen this before where they do I versus V, and you'll get a slope here as well. But the slope is not resistance. What the slope is here is 1 over the resistance because they've switched the XY axis, so you have to switch the slope. Here's a quick simulation of Ohm's law. It's written so that it's V equals I times R. And you get to see here, here's a circuit, and if I increase the voltage, in other words, if I add batteries, the voltage goes up, and I'm keeping the resistance constant so that you can see that the current goes up as well. The current will increase. And if I increase the resistance, though, that current will go down and make the resistance larger and larger, that current goes down. So there's these inverse relationships here and direct relationships that we have to understand. So we're going to look at page 74, number 28, and do an example problem here. It says the aluminum wire in a high voltage transmission line is 2.7 meters in diameter. It's designed to carry 1100 amps of current, and we want to know what's the voltage drop across a 37 kilometer long segment of this power line. So since I want to solve for voltage drop and we have current, what I can do is use V equals I times R. That's Ohm's law. I know the current is 1100 amps, but what's stopping me from solving this problem is resistance. But I've picked this problem also because we're using the resistance of the wire and Ohm's law together to help us solve for this voltage drop. So now we can solve for the resistance of that wire by using this equation here. R equals rho times L over A. So let's go ahead and plug in our values. R equals, oh, wait a second here. It's aluminum, so I have to look up resistivity of aluminum. That's 2.7 times 10 to the negative 8th. And that's in ohm meters. The length of the wire is 37 kilometers, which is, we have to put in is 37,000 meters. And the area of a wire is since it's a circle, we have to go ahead and do pi r squared. Now the diameter is 2.7 centimeters, which is really 0.027 meters, but the radius is what we want. It's half of that. It's half of 0.027. which is 0.0135 meters. And so we'll go ahead and, so for our area, we'll do pi times the 0.0135 meters squared. It's our pi r squared. And so we'll come up with a resistance equaling 1.75 ohms. And so we go ahead and we can put that up here, 1.75 ohms. And so our voltage is 1100 times that 1.75. And we end up with 1920 volts. Well, it's 1920 amp ohms, which is the same thing as a volt.